welcome everybody. I want to welcome everybody to the First Coast Free Thought Society Zoom Room. The First Coast Free Thought Society is an organization of individuals who prefer science and reason over religious dogma and fanaticism. We've enjoyed the non-religious community of Northeast Florida and beyond since 1998. We are also the proud Jacksonville chapter of the American Humanist Association. We are part of a coalition of nonprofit organizations who have come together to advocate for a connected network of parks and green spaces in downtown Jacksonville called Riverfront Parks Now. We're on Facebook, X, Meetup, Instagram, and YouTube. We meet in person, socially, through our secular Sunday gatherings in the park, book and movie discussion groups, and sometimes at a local watering hole, which next will be this coming Wednesday, November 20th, for a post-election happy hour or tragic hour at Firebirds in the town center. And our next movie discussion is Tuesday, November 26th at 6:30 p.m. right here in our Zoom room when we'll chat about the 1980 film Resurrection. Our next book for discussion is on December 7th, Adam Smith's America, How a Scottish Philosopher Became an Icon of American Capitalism by Glory Liu. Our Freethinker newsletter is published monthly, to which we invite your readership, feedback, and submissions. A reminder to all contributors, submissions for our December edition are due this weekend. You may learn all about what I just mentioned at our website, fcfs.org. So welcome everybody. I'm very glad you're with us. We're all volunteers, yet we do incur some expenses, largely promotion. We have promoted online, on the radio, direct mail, and in print. And if you know of a viable place for us to promote, please share it with us. We also have some associated costs for website and fees, regulatory compliance as a 501c3 charitable educational organization. So if you can offer a small membership donation of $15, $20, or any dollar amount, you'll be part of the reason we're able to continue our public outreach. We are tremendously grateful for all who have made donations. We need you and we appreciate you. Now, next month on December 16th, we will meet in person at the Olive Garden on Phillips Highway in Jacksonville for our annual Human Light celebration. Please RSVP on our meetup page so we can get an accurate reservation head count. On January 20th, 2025, our speaker is scheduled for a return visit, author Catherine Stewart, who wrote several books, including The Power Worshippers Inside the Dangerous Rise of Religion Nationalism, which also serves as the basis for the documentary film God and Country, which we watched as a group last month. Sign on to our meetup page, sign up for our newsletter, and email announcements at our website. Stay in touch. If you have an idea for a speaker or other programs, please let us know. Now, tonight, we are pleased to welcome our distinguished guest from the University of North Florida, Dr. Lev Gasparov. Dr. Gasparov is a physicist with a research focus on optical spectroscopy and material science. His journey has taken him from Russia to the United States with a significant stint in Germany as a visiting scholar and Alexander von Humboldt Fellow. He has been at UNF since the year 2000. He is well published and his peer-reviewed papers have been cited over 1,400 times. He has also secured substantial grants facilitating the advancement of his critical research projects. It is our hope that Dr. Gasparov will offer us a primer about why physics is important and then dive into his area of expertise. So there's a Q&A feature down below and a chat feature down below. It's a little different than what we're all accustomed to. You don't have to mute your mics. I think everybody is muted automatically. So, but please know we are recording for this presentation for posterity and uploading to our YouTube channel. As a side note, we are open to the public. We don't know what might be said during our Q&A discussions. Sometimes we cringe, sometimes we nod in quiet approval, and sometimes we cheer. We always look forward to a robust civil discussion. Now let's begin by appreciating Dr. Gasparov for graciously offering us his time, expertise, and insights. So Lev, we are all yours. Take it away.
Well, thank you so much. Thank you so very much. It's an honor to be able to present to general public, because typically as a researcher I would present at the conferences or to the students, but I think as any reasonable and any responsible scientist, we need to talk to the general public and show why science is important, what does it accomplish, and so on. So I'm really happy to be here. So what I'm going to talk about, my research, and the subject of the talk is high pressure optical spectroscopy at UNF. I've been doing this for quite a while, and as Ken mentioned, I was born in Russia, in Soviet Union, actually, not Russia, in Soviet Union, and very often I joke to the folks who ask me where I'm from. I'm saying I'm from Jacksonville, and the accent that you hear is a typical North Florida accent. Of course, they smile. So the old country is Russia, and my education, my master's and bachelor's and PhD all came from Russia. It had a reasonable educational system. And in the 90s, I was fortunate to get a chance to work in Germany in a wonderful group of Professor Günther Roth in Aachen. It's on the west of Germany. And after that, I received an appointment as a postdoc at the University of Florida in Gainesville. And after that, I was fortunate to get a faculty position at the University of North Florida. I'm in awe of U.S. system of higher education. I think it's wonderful. It provides so many opportunities for so many people. And I just hope that more people would take advantage of that. With that said, I would like to talk about my research. So as I said, my research is high pressure optical spectroscopy. But let me uh, go into a little bit of detail. So I already talked about my background, so I'm going to skip this slide. And Ken graciously talked about my accomplishments, so I guess I can skip through this slide as well. What is optical spectroscopy, and why it is important, and how it is being used? Well, optical spectroscopy, in a nutshell, what you do, you shine light on something you want to study, and then you analyze what comes back. And your goal is to use this light that comes back to figure out what is happening in that material that you study. And you can study all sorts of different materials. Now, the huge advantage of the optical spectroscopy is that it is non-destructive. So in other words, if you have the sample that you're studying, you can put it in your setup, make your measurements, and then take it out and use another technique to probe the same sample. And that's huge advantage because there are other techniques like analytical chemistry when you can study what's inside the material, but you dissolve it, and after that, you cannot reuse this material. So that's a great thing about optical spectroscopy. In addition to using light, what you also do, you want to disturb the sample because usually you're interested in the phenomenon that this particular sample displays. And there are many phenomena that related to conductivity, related to magnetic properties. So to disturb this, you can use temperature or pressure, and those disturbances allow you to see what happens with the properties of the sample while you change the parameters of your experiment. And then helps you to look into the inside the sample, so to speak. So in a sense, that's the idea of optical spectroscopy. And as I mentioned, it is related to, it studies samples, so it's material science. And of course, there are many materials to study. So what I'm using so-called Raman spectroscopy and Raman scattering. It's called Raman after the Sir Chandrasekhara Venkata Raman, or C.V. Raman as he is known in India. He is a recipient of Nobel Prize in Physics from 1930, and he is the first Asian recipient of Nobel Prize. is very inquisitive gentleman, and one of his discoveries that was preceding Raman scattering was related to the color of seawater. And he was curious about that because during his vacation, which also reminds us that it's important to take vacations. So during his vacations, he looked at the color of Mediterranean Sea, and he was trying to explain why there is that such turquoise color, because the previous explanation for the color was, well, that this is because the sky is reflected in the sea, and that's why it is blue. So, and he looked at it and said, well, not doesn't look like that's true. And he actually published a paper on that. So that tries to explain the color of the sea from the point of view interaction of light with the molecules of water, not just a reflection of it. That was only one part of his work. The part which led to the Nobel Prize was related to their so-called Raman scattering. And here's the idea of it. I'll try to show it with this cartoon. So what you have here, you have incident light. This green arrow indicates this incident light that impinges on the sample. And some of the light is reflected back, or scattered, rather scattered back, with the same frequency of as an incident light. And by the frequency, you basically mean color of the light. But there is some fraction of that scattered light that changes its frequency. And that change happens because the light, incoming light, interacts with something that happens in the sample. And in this particular example, it interacts with the vibrations of atoms. So what you expect is the following. You have incident light. So that's what you see here on this panel is so-called spectrum. So in a spectrum, you have intensity along y-axis and frequency along x-axis. And I'll talk about units for the x-axis later on. So I mentioned that you have incident light. There is one condition that is critical for Raman scattering, and that is that this incident light should be monochromatic. Monochromatic means it's one color, one frequency. So in an ideal world, that would be a laser light. So laser has one color, one frequency, and that's what is directed to the sample. Now, the scattered light will have frequency that is different from laser frequency. So there will be side bands. And those side bands, that's what Raman discovered. And that scattering gave him the Nobel Prize, so to speak. And that's technique that is frequently used in many, many areas of material science. The important point here is that the number of Raman lines in the spectrum is determined by the symmetry of determined by the structure of a particular sample. So in a sense, Raman spectrum is a fingerprint of a particular compound. And that helps, that is very useful for many different applications. So here's an example of Raman spectrum on the material that was interesting to me. So what you see here is y-axis, which is basically intensity of the signal, and on x-axis you see something that is called Raman shift. And it's in this funny unit centimeters minus 1, or sometimes it's called wave number. And I'll talk about how it is related to other units. So the something that is at the zero frequency is going to be laser line. You don't see it because laser line is actually about 14 orders of magnitude is stronger than the signal that you see in the spectrum. So there are some technical tricks that allow you to cut this laser line from the spectrum and allows you to see Raman lines. What you also see here that those spectra are taken at different temperatures, and there is certainly change in the spectra as you change the temperature. And I'm going to talk about it a little later. Excuse me. So few words about x-axis. What's on x-axis? This 1 centimeters minus 1, that's one Wayne number, is the unit of energy. So, excuse me. So in a sense, it is related to other units of energy. And now those units include milli-electron volt, Kelvin, which is the unit of temperature. And they are related by the equation that energy is equal to frequency of radiation times Planck constant. Those are different conversion factors. So something that might be useful to remember is about 200 wave numbers corresponds to the energy associated with 300K. And 300K is something that is that is equivalent to the room temperature. So just gives you an idea about scale on the x-axis. But what's important here is that's energy. So what can we learn from Raman spectroscopy? We can certainly detect ion vibrations. We can, and that because the number of vibrations is determined by the crystal structure. Those modes, they manifested by Raman lines, by those peaks. Now, when crystal changes its structure, then the Raman spectrum changes. So that can also be used as the measure of some sort of phase transition. So here's the Raman setup that I have. So what you see here is so-called CCD detector. It's similar to what we have in our cameras, except that this one is cooled with liquid nitrogen because the noise of detector should be very low so that we can detect very low light signal. The machine itself is a spectrometer. Its job is to disperse the light that comes from the sample into the spectrum. And it does that with the help of diffraction gratings. Now, what you can also see, aside from the student, and I'm going to talk about student later on, you can also see the helium dewar, liquid helium dewar, which is connected by the transfer light to something that is called a cryostat. That device allows you to change the temperature of the sample. So in that setup, I can change the temperature of the sample and see how the Raman spectrum changes while I measure at different temperatures. What I can also do, and I'll show it later on, that I can also change the pressure that is applied to the sample, but that's a little later. So the material that I'm interested in is magnetite. It's a material that you can actually find on the beach. If you go to the Jacksonville beach, take a magnet, stick it into the sand, most likely you will get dark particulates on the magnet, and those particulates are magnetite. And so this is very interesting material. The formula of it is very simple, but material is not simple. It's actually quite complex, and I'm going to talk about its structure, crystal structure. And what's interesting about this material, it has this phase transition that was discovered in 1939 by Verwey. Naturally, it's called Verwey transition. So the mechanism of this transition remains unclear for more than 80 years. So this material is a puzzle, and I was interested in this material, and that was part of the work that I've done here, and also with my colleagues in geophysical laboratory. So there is a side note about magnetite. I mentioned that you can find it on the beach, and the reason is that there is this bacteria which is called magnetotactic bacteria that have magnetite as a part of their guts. And the reason I have it is because they can align themselves along the magnetic field lines of the Earth, and those magnetic lines of the Earth point towards bottom where food is. So those magnetic nanoparticles allow bacteria to orient themselves in a way that they can reach the bottom of the reservoir where the food is located. So it's very interesting way how nature explores the property of material that has nothing to do with a life form, but it can be a part of a life form. So I found this to be fascinating, actually. Very transition. I mentioned very transition magnetite. So what you see here, you see the graph of conductivity of magnetite as a function of temperature. On x-axis, you have temperature measured in Kelvin, and just to remind you, 300 K is about the room temperature. 0K is very cold. So it's basically not negative 273.15 degrees Celsius. The scale on y-axis is conductivity, which is opposite to resistivity, which basically tells you that whether material is good conductor or bad conductor. So what you can see here is that above around 120 degrees, the material is not a bad conductor. But then at 120 degrees Kelvin, the conductivity of material drops. And this is logarithmic scale, so the drop is 2 orders of magnitude. So had I drawn it in linear scale, that would be just a very sharp step. And that just to show how things change at the lower values of conductivity. So there is this transition between metallic state and insulating state. And the mechanism of this transitions was something that was interesting to me. So few words about crystal structure of magnetite and what happens at the Veritway transition. In solids are characterized by so-called long-range order. In other words, there is a pattern there that repeats itself and repeats itself on many periods. And the smallest volume that repeats itself is called unit cell. And that unit cell is characteristic for a particular compound. So for magnetite, this unit cell is a cubic unit cell, and it's rather complex. So what you have here is following. You have iron atoms, which are in so-called A sites, and those 8 sites have tetrahedral oxygen coordination. The blue circles indicate oxygen. The brown circles indicate iron on B sides, which has octahedral oxygen coordination. So the initial idea of the Veritway transition was related to the ordering of atoms on A and B sides. And when that happens, then the understanding was that that leads to the insulating behavior. So when transition happens, there are many things that change in addition to resistivity or conductivity. Magnetic properties change. There is a change in specific heat and many other properties. Now, if you try to figure out what's happening with the crystal structure of magnetite, you quickly find out that the unit cell, that smallest volume that repeats itself in the material, becomes bigger. At the beginning of the talk, you probably remember that I mentioned that the number of Raman lines that you see in the spectrum depends on the crystal structure. So if you have bigger unit cell, you expect to see more Raman modes. In other words, you could expect to see the phase transition in the Raman spectrum. And that's pretty much what you see. Here's the graph of the magnetite spectrum, which shows one spectrum which is recorded at 125 K above the Veritway transition, that's in black, and another one at 50 K, which is in blue. So what you can see immediately that the blue spectrum has additional lines, and that's the indication of transition. And you can do much finer job in studying this phenomenon. So you can change temperature with small increments, and you see that its transition is quite abrupt. So those additional modes are clearly seen. So that allows you to immediately indicate, find the transition using Raman scattering. The next thing I'm going to talk about is phase diagram and which is related to this phase transition. I mean, we all know the states of matter, so liquid, gas, solid, and that can be represented on the phase diagram where one axis is pressure, another axis is temperature. Those two cartoons, they indicate two fairly famous phase diagrams. The one on the left is phase diagram of water. So you see this triple point of water at 0 Celsius, it's where it freezes. That's the boiling point. That's the freezing. When you cool water, it becomes ice. Now, if you increase pressure, the structure of ice changes, and there are actually many modifications of ice. So as you can see, the phase doesn't have to be transition from liquid to solid or from solid to vapor. It can be a transition from one structure to another structure, and that's example of magnetite. The one on the right is phase diagram of carbon, also quite famous. Now you can see here that at reasonable temperatures, so that's in thousands of Kelvin, the thermodynamically stable phase of carbon is graphite. And then if you increase pressure, you can finally get to the diamond. Now, it's interesting to note that diamond is not your thermodynamically stable phase. So if you wait long enough, then diamond should become graphite. So I don't know whether you remember it, but some years ago, there was this advertisement that diamonds are forever. I always look at that and say, no, that's a lie. They're just for 10,000 years. After 10,000 years, they will become graphite. In any event, also the temperature, here you have conversion between temperature in Kelvin and temperature in Celsius. And here's another thing to remember. 22.20 Celsius is about 300 degrees Kelvin and about 72 degrees Fahrenheit. And of course, degree of Fahrenheit is not exactly the same as a degree of Celsius. It's about half of a degree of Celsius. Okay. So in my case, in my research, I'm interested in the phase transition between two phases of magnetite. Why am I interested in that? Well, pressure is another variable that can establish the mechanism of the transition. So there is a theoretical prediction that is based on charge ordering. And there was a long discussion, a long dispute over there is charge ordering there or there is no charge ordering. And one of the theoreticians came up with a model, and that was testable model. So in other words, what he proposed was that the slope of the phase diagram, phase separation line can be given by this number. So all those parameters can be calculated or measured, and this parameter, the slope of the line, can be measured if you know phase diagram. So to me, to test this experimentally, and I'm experimentalist, to test this experimentally, what I would like to do, I would like to find how variable transition temperature changes with pressure, and then see whether the slope of that phase diagram separation line is similar to what's predicted by the theory. That's very often what happens with science. You have a theory, but then you have an experiment that either disproves the theory or confirms it. So that's a classical scientific method. So pressure is defined by force per area, and pressure has many different units. The System International units of pressure are Pascal, and it's 1 Newton per meter squared. Well, of course, there is one atmosphere. It's around 101,000 pascals. 1 bar, which is 100,000 pascals. 1 torr, which is about 133 pascals. 1 millimeter of mercury, which is very close to 1 torr, very, very little difference. 1 psi, which is about 7,000 pascals. Now, the pressures that I'm working are close to gigapascals, so it's 1,000 million pascals or 10 kilobars or about 10,000 atmospheres. Just for the reference, the pressure inside the Earth's core is about 364 gigapascals. So high pressure experiment that I'm running is between 2 and 25 gigapascals. It's not as close, not too close to the pressure in the center of the Earth, but it's quite high pressure. And I'm going to talk about how this can be achieved in the experimental setup. So as I mentioned, the goal of my experiment is to create pressure temperature phase diagram, which I can do with the help of a Raman experiment, and use the slope of this line to compare it to the theory. So how do we create high pressure? To create high pressure, you need a setup which is called diamond anvil cell, or DAC. So it is literally consists of 2 diamonds. You can see them there. And there is a gasket that has a small hole. The hole is about 200 microns. This sample, you have to get your very small sample, about 20 microns across. Put it in the hole. Put little pieces of ruby that you can use to measure high pressure. Then fill this with an inert gas such as helium and close this, basically apply force to those diamonds so that they create so-called hydrostatic pressure. In other words, the small volume you can barely see on the slide is squeezed from all sides. That's why it's called hydrostatic. So then you have a system of nuts and bolts that transfer force to the diamond anvil cell. So basically, you squeeze those 2 diamonds. You know, to create high pressure, you need to have some force and very small area. And since this hole is very small, you have quite small area. So with a reasonable force, you can create very high pressure. And then you can put this whole thing inside of cryostat. So not only can you change the pressure, but you can also change the temperature. Now, the loading of this diamond anvil cell is quite an ordeal. So it sometimes takes a week to do that. And I wouldn't be able to do it without a colleague of mine who worked in a geophysical laboratory in Washington, D.C. So that was a great help, and I'm very grateful to him. His name is Victor Strushkin. He retired from geophysical lab. So this is the setup that is a little bit different from what I showed, but it's very miniature, and it allows you to do pretty much the same. So this is diamond anvil cell. You can barely see 2 diamonds here. This plate is a gasket. So that's the face of the cell. So you shine light through the diamonds on the sample, and you collect light scattered from the sample and analyze it. And that's where you see your Raman scattering. And so when you do it, you can do several things. For instance, you can keep pressure constant, and then you can change the temperature. And when you see additional lines popping up, you can immediately say, hey, this is where transition temperature takes place, because new additional lines, that means that the sample is in its less conducting state because I know that its structure becomes different, its unit sense becomes bigger. What you can also do, you can keep the temperature constant and change pressure, and that allows you to, again, to find the temperature, transition temperature as you change the pressure. So that allows you to go around different, to measure different pressures and temperatures and create this phase diagram. And again, the trick is to see where, to detect additional lines. If you detect those additional lines, this is where transition takes place. So this is the result of the several experiments, and it's pretty much this line that separates metallic phase from semiconducting phase. So there are two phases here. As you can see, the pressure went from 0 to 25 gigapascals and temperature from 0 to 120 K. So at room temperature, the transition is 120 K. As you increase pressure, the transition drops. From this graph, you can figure out the slope of the line, and then you can compare it to the prediction of Brabers. So the high pressure Raman experiment yields slope of the line that is around 5 Kelvin per gigapascal. What Bribers predicts is about half of that. Now you can ask, well, that's not such a great comparison, great agreement. Well, in condensed matter physics, the agreement within an order of magnitude considered to be good. So even though this agreement is not ideal, but it's pretty remarkable. So that is an argument in favor of charge ordering-based mechanism of this transition. So in a sense, that completes the research part of the presentation. In the few following slides, I would like to talk about my students. As a member of university, as a university faculty, you do research, you create new knowledge, but you also teach, and that's a big part of the job. And I was blessed with many students who work in my lab. This is a list of them. It's not exhaustive. I'm actually missing a couple of students here. Some of the students came back and are actually now working as assistant professors at the University of North Florida. So this is very rewarding to see your students come back and get their PhD somewhere else. Now, what I would like to talk about this guy whom you already seen. This is Andrew Rush. I'm obviously proud to have him in the lab. He graduated UNF physics program, bachelor's program. Then he went and got patent law degree in Stetson University. And then he became president and CEO of Made in Space, the company that made three-dimensional printers that allowed to print some tools at the International Space Station. Then he helped to sell this company to another company, which is called Redwire. And in 2023, he became a president and CEO of another space-related company. So that's very rewarding to see the progress of this gentleman and his contribution to the promotion of science and development of spatial technology and things like that. So I wanted to mention this. This work wouldn't be possible without my collaborators. So you have to have samples grown somewhere. You have to have collaborations with different places. I already mentioned Victor Strushkin, who was my great collaborator at Geophysical Laboratory. He is no longer working there. He has retired. I was fortunate to work at the University of Florida in the laboratory of David Tanner, great professor. I was blessed to work in his lab. There are also results of collaboration with the University of Technology in Troyes, France, with my colleagues in Aachen and colleagues in Lausanne. Actually, the samples came from Switzerland in Lausanne. So that concludes my presentation. So I would like to thank you so much for your attention. I hope this was informative and interesting, and I'm happy to answer all your questions. Oh, at least I will try. I will attempt to do that.
Okay. I appreciate that very much. If you do have a question, I think we have to put it into the Q&A area, and I can read it out, and we'll see how that works. But I can get us started a little bit, I think, maybe. I don't know. It was very complicated. Can we just, from my perspective, because obviously I'm a lay person, I took high school physics, and I enjoyed it a lot, but that's the extent of it. So can we start by you offering us a description of what physics is?
Physics is a science. Well, good question, right? So physics is so many different things. You have condensed matter physics, which studies materials that are solid. You have high energy physics that studies particles like Higgs bosons. You have cosmology, which tries to predict what is the how the universe was created. So there are so many different things. It's a science of nature, I would say. I think that would describe it. I think that would be reasonable description. I don't know whether that's the best description, but it's a science that wants to describe the nature.
Hmm.
Yeah,
And
something.
that seems like a very simple
Yeah.
explanation, and that's usually the best way to go. Um, uh, you spent a lot of time talking about light, and I've got some questions about light in general. Can light bounce off other light?
So there are examples of interaction between laser beams. So uh, I remember reading about that. So if you have two laser beams that are very high power, I think there are conditions when those can interact. In the typical everyday situation, that doesn't happen. For instance, with the light can actually exert pressure. I mean, we are not thinking about that, but that can happen. For instance, there is this so-called LIGO observatory, which observes gravitational waves. So what they do, they have interferometer. Interferometer is basically a machine which has mirrors that are at certain distance, and it can measure the variation of the distance between those mirrors. Now, they shine a very powerful laser between those two mirrors, and that laser exerts pressure significant enough to affect the position of the mirrors. So
Hmm. We have a question from in the Q&A. We got a couple there. I'm going to read one. Are you excited to see what the Clipper is going to capture when it reaches Europa? From what I understand, it has a mass spectrometer on board. Is a spectrometer different than what you use?
So mass spectrometer is a little bit different. So what mass spectrometer does, it tries to, I mean, the idea is the same, to figure out what's inside, what's the material that you study, but it's done with a different techniques. So mass spectrometer basically uses magnetic field and ionization of the material that you put inside and tries to see what kind of material is that with that help. Um, so it's let me try to make it less complex, if I can. Uh, Mass spectrometry is called that because it tries to measure the mass of the ions that are created from the sample that put in this spectrometer. So if you have, let's say you have a robot on the surface of Mars, right? It can grab a little bit of Mars dust, put it in a spectrometer, switch it on. That spectrometer will ionize this dust, and those ions will bend in the magnetic field, and the way they hit the detector depends on the mass of the ions, and that allows you to figure out what kind of material was put in spectrum. I don't know whether that
Uh-huh.
helps, but I
Okay. Well, we have another question from the Q&A from Lance. He happens to be in Thailand right now. Are there advantages to manufacturing products in space to manufacturing products on Earth?
Actually, yes. So, for instance, there is a fiber, optical fiber, that is very expensive, and the one that you can manufacture in space because of the effects of gravity. The fiber typically has to have some gradient of the index of refraction, which allows you the way the fiber works is the light bounces off the walls of the fiber. And the way it bounces depends on the material that fiber is made. And there are some fibers that have very specific index of refraction, which are difficult to make at the surface of the Earth, but it's easier to make in outer space. So that's one thing that is used in outer space. That's what I learned from my interaction with Andrew Rush.
Hmm. This next question is in the Q&A is from Dr. David Schwambert, who spent a long
Oh,
time at UNF, and he wants us to be reminded that he is a political scientist and not a real scientist. So here's his question. Let's see. When you are looking at the transition phase of magnate, it seems to me that the kind of information you get and might apply to other minerals and metals might let us know, for example, that if we want to use a certain mineral for special uses, we will learn that we can only use it in a certain state, pre-transition or post-transition. Is this a possible practical application for this kind of research?
it is possible in practical application, but actually having a transition can be very helpful. For instance, if you have very sharp transition, that is a function of temperature. And by the way, David, I hope you're doing fine. I'm very well. Remember David Schwamberg, and I hope that you have a very fruitful and exciting retirement. So uh, yes, definitely to have a transition is actually quite helpful. For instance, if you have very sharp transition and you have a little bit of heat coming to this material that exhibits the sharp transition, that little bit of heat will move the material from one state to another state. And that allows you to figure out how much heat impinged on the material. So in other words, you can measure the amount of heat coming from some source. So that can be used for myriads of applications.
Uh, okay, and Lance has a follow-up to his earlier question. And what would you do with these fibers?
So usually the fibers, so when you use fibers, one of the issues with fibers is that they attenuate the signal. So if you think about it, you have a cylinder and the light bounces off the walls of cylinder. And you can think of two paths of light, one that has more bounces and one that has fewer bounces. Those two paths of light, they send the signal. So something that comes as a sharp pulse at the one end of the fiber will become broad pulse at the other end of the fiber. That's not good. You want to have pulse as sharp as possible because pulses transfer the information. And you don't want your information to sort of become less defined.
Hmm.
So those fibers, they allow you to make very weak attenuation, meaning the signal can travel at the very long distance with very small distortion. So that's the goal. So, or because if you don't have that, you have to put the amplifiers at certain distances, at couple of miles, you have to put an amplifier. That's additional expense, additional work. So that's why it's important to have a fiber with the right index of refraction and with the right type of index of refraction, because you can have fiber that have difference in the index of refraction depending on the whether it is in the center or on the board, on the edges of the fiber. So
And one last follow-up from Lance, and we'll go to Mary. What could you make with this material? What product?
do you mean magnetite or you mean the fiber?
Mm-hmm.
Uh,
Yes.
with magnetite, potentially you can use magnetite to create devices which are called spintronic devices. So that those are devices that can potentially change. So how do I change electrical properties with the help of magnetic properties? That's the broad explanation, and that can be helpful for computer industry.
Mm-hmm.
It's very general answer. So, but there are some practical applications. Usually those are you need to have a thin film of this material because typically you don't use the bulk sample.
Um, a question from Mary Wall. Let's see. Mary asked, yeah, it is a question at the end. It looks like there is some connection to the question of the origin of life and the operations of physics in doing so. That might include currently AI and the possible creation of bioengineering creating sentience.
Oh,
Yeah,
uh,
I mean, maybe that's enough said.
uh, well, I'm not I'm not sure what I can say of that. I
It,
mean, creation of life is something that is, you know, this is one of the fundamental questions. How did we end up on this planet? I mean, that's a very interesting question, and I don't know whether we have a very conclusive answer to that question. So I wish I knew the answer to this question, and I hope I will be able to learn the answer to this question before I reach a certain age. But
Right.
yeah,
Well, it's a huge question, and it talks about all sorts of things that,
exactly.
that might, one of my favorite answers to a question is, I don't know.
That very good. I agree with you.
Beats me.
Yeah, I agree with you.
Um, this is from an anonymous attendee. Is there a universal formula for measuring gravitational force? And is it the same on, say, Mars as it is on Earth? I guess relative to the formula.
So yeah, it depends on the mass of the planet. Basically, it's you can calculate the so acceleration of free fall on surface of the planet. You know the mass of the planet and radius of the planet. So that's something that is relatively not difficult to do. Yeah, that you can do that.
When you opened your presentation, you talked about um, how to shine a light. The definition of what you do: shine a light and see what comes back.
Hmm.
That's you in a nutshell, in a very simple
Yeah.
way. So I
Uh-huh.
was thinking, could I work in your lab? Because I have used a flashlight, and I've used a flashlight to shine a light and see what comes back. Big difference,
You
right?
you don't have to use flashlight because I have lasers, but you can certainly work in my lab. That's not a problem. I mean, uh,
All right. So all right. Are there massless particles?
I think so. I think so. I'm delving here in the area of high energy physics, which I'm not an expert, but I think so.
Mhm. Can light bend?
Yes, 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 it can. So actually, gravitational force can bend the light. Yeah, yeah, and that's it's interesting. Yeah. So, I mean, uh, one of the ways the light bends, so bends in quotes, is when you use the prism, right? So that's one way of for light to bend because of the difference in the indices of refraction. So, for instance, if you look at the fish at the bottom of the pond, the fish is not located where you think it is located, but it's located in a different place. So there is a bending of light. I don't know whether that's the bending that's interesting,
Mhm.
but yeah, definitely.
And the photons, when we see light coming from deep space coming to
Mhm.
us, and it spreads out eventually. It's
Mhm.
not laser focused any longer. It
No.
gets wider. Does the space between the photons get wider? I mean, within the photon get wider as well?
So the photons, you can think of photons as a particles. So particles arriving to there is a duality of the particles. The particles can be described as a wave and as a particle. So the electromagnetic radiation can be described as a particle and as a wave. So when one says that distance between photons is different, I think one can think of it this way, but again, because it can also be a wave, you can say, well, the wave is just gets less intensive because if you think about the source of light, then it radiates in all the direction, and the further you go, the less intense it gets. But the wave, the repetition of the wave is the color of the light. And color of the light doesn't change as you move away. So, I mean, the light that's reflected from Mars is still red. It doesn't get different color when it reaches the Earth. So, I mean, that would be my answer. I don't know whether I answered the question, but that's
Yeah, yeah. You made an off, yeah, a little a joke about diamonds are forever. And then you told us that that's not true. Diamonds turn into graphite after about 10,000 years. So I started thinking about our number two yellow pencils, and could we reverse engineer this and turn the graphite back into diamonds?
yes, we can, but they need to apply a lot of pressure and
Right.
high temperature.
And so you would be the guy, right?
No, I wouldn't be the guy, but I could probably hook you up with somebody. Well,
That's
there's actually, I remember when I worked in Gainesville, there was a company there that was working on artificial diamonds. As a matter of fact, the best diamonds for diamond anvil cell are synthetic diamonds because they don't have inclusions. Because inclusions create additional spectral lines that interfere with your spectrum. So General Electric was very successful in growing artificial diamonds, and those were used, very often used in those diamond anvil cells. I remember back in the old times, the colleague of mine will bring a plate with 16 holes. Each of those holes would have a diamond, not artificial diamond, but natural diamond. And we would test it on the type of a diamond, whether it was pure enough to be used in diamond anvil cell. And so it's kind of weird to see this little thing with a bunch of diamonds on your table. So for somebody who is not a jeweler, that was fairly bizarre.
uh-huh. Yeah. Well, they used to use diamonds in phonograph records to capture the sound on the
Hmm.
albums. They used to
Oh
be
yeah,
done
yeah, 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 yeah.
right. And Superman, by the way, he was able to crush coal and turn coal into diamonds.
Well, yeah. If you apply high enough pressure and high enough temperature, you'll get diamonds.
Mhm.
Absolutely.
Mhm.
Phase diagram just told us that.
Um, there's a comedian, Stephen Wright, and he talks about the speed of light, but he questions what the speed of dark is. Is there such a thing?
I don't think so.
No, no speed of dark. Okay. Are there any other Q&A questions? Let's see. There might be. Let me look. We do. If um, We have another question from David Schwambert, who
Uh,
wants to know, since you work with lasers
uh-huh.
in your lab regularly, do you have trouble with cats? You
Cats?
know how cats love to chase lasers around?
Oh, yes, yes. I have a cat. No, I have a cat at home, and my cat loves lasers. I mean, every evening I have to play with the cat with the laser, and that's the routine. Otherwise, I will not get a good night's sleep. The cat will be complaining.
Mm, okay. Well, if there are no other questions, then I think maybe it's time to say thank you very much to Dr. Gasparov for a wonderful presentation. I hope some people learned something. I know I did. This is going to be uploaded to our YouTube channel. You can probably download it from there if you choose to, or you can watch it as often as you like, take notes or whatever you'd like to do there. But I very much appreciate your time, your expertise, your insight, your patience with us. And I want to remind people that this Wednesday at Firebirds in the town center, starting at 4 o'clock, going to 7:30 for happy hour or tragic hour, depending. It's a post-election get-together. And then next month, in December 16th, we'll do our Human Lights celebration. Please RSVP at our meetup page so we can get an accurate head count. And I'm going to give you a big round of applause. I
Oh,
thank you.
thank you so much. Thanks so
Thank
much.
you
I
so
hope
much.
that was interesting.
All right. All right. Everybody saying thank you. Great talk. Thank you.
Oh, thank you, thank you.
Thank you. Bye bye now, all.
Bye bye.